welcome everybody. We are very happy today to have Vincent to talk about 3 flavors of H fields.
So thanks for the invitation. So I'm going to talk about other differential fields, as models for real value differentiable functions. The idea would be to present 3 types of models for such functions, 3 types of what is called H fields that are different but really closely related. I will start by introducing some basic context and presenting results from other people, and at the very end of my talk I will talk about what I did. So first we are just to set the context, we are working with another group, a linearly ordered abelian group. We are considering some structure in this group, so a set of functions with finite variety. We call this structure an ordered algebraic structure, so operations and a linear order. And so we can consider the closure of this set S and the composition of composable functions, including those projections which identify two. So, for instance, you can say you could send AB to AA, for instance, this type of stuff. So this is just a way to do model theory, so to consider terms, first order terms, without really doing model theory. So if we are introducing an order on the structure, this imposes some constraints. The first one is, how should the functions behave with respect to the ordering? So in the case of differential fields, we'll have so the group operation, the product, and the derivation, and we would like to know when do we want this inequality to hold, for instance. And secondly, having an order imposes some restrictions on which equations can have solutions in ordered structures. So for instance, you cannot include the solution to this equation in an ordered field, because it will violate the ordered fields axioms. So in our case, if you're looking at the differential field, an ordered differential field, if we impose this relation here, so when an element is greater than the constant field, we want the derivative to be positive, then this simple differential equation cannot have a non-zero solution, for instance. If we don't impose anything, we could give solutions to those equations, but this is a way to impose that we don't have things that behave like cosine and sine, for instance. So to be more precise, I will consider 3 types of actions on the structure. This is really vague stuff. I'm not doing really model theory, but it would be equalities, which would be saying when some term cancels, so is 0. Inequalities, which would tell when some term is positive. And then equations, which will tell when some equation, this thing here, has a solution. So when there is some term B, such as this is 0. So to give examples, if we take an ordered abelian group, we can have as equalities and inequalities the axioms for ordered abelian groups. Although, you need also equations for the opposites. And if you want to look at abelian groups which are closed under various equations, then a natural set of equations that you can consider is those linear equations here. And if you close the group under those equations, then you get a divisible ordered group. And this is a nice closure property, because divisible ordered groups are what is called existentially closed ordered groups, meaning that if you extend another group into another other group, if you have term in the first order group that is 0 in the second order group, then it will be 0 first in the first order group. So another example is in the case of ordered rings. In that case, we want the actions for ordered rings. And if you want this existentially closeness notion, then we have to take what is called real closed fields. So we will have solutions to those equations. This will be minus to those equations, and also to those equations which are just saying that polynomials with odd degree have zeros. So in our case, we are looking at other differential fields. So we want the actions for differential fields or rings, actions for ordered rings, and then we are free to choose what we want in terms of inequalities and equations. And there are several solutions that we can choose. So the first one I wanted to mention is imposing no compatibility between the differential structure and the ordered field structure. So you only take separate actions. And then you get a nice existential closure, which is if you there's a theory, which is a model completion of this theory, which was described by Singer, which basically says that you have solutions to equations, the differential equations, for which it is consistent that they have solutions as algebraic equations. It's a way to rephrase this. We will choose another solution, which will be looking at structures that behave like fields of differentiable functions, real valued differentiable functions. And our closure equations will be what I would call intermediate value theorems. That is, you take a term here with only one variable, and you assume that it changes its sign between two elements A and C. Then the equation T of B equals 0 should have a solution. So you want an intermediate value theorem for those type of terms. We will see that we can have consistent theories of differential fields with this type of closure. So our models of differential fields will be differential fields of real-valued functions, as I said. So what you would want to take it ideally would be smooth functions. And we would want to have a pointwise operation, so pointwise sum and pointwise product. We would want this to be a field, a differential field, and an ordered field. So if you want to really have a field, it means that the functions cannot have zeros because you are taking pointwise products. And so if you want to have to make sure that functions can not be zeros, then it's easier to take germs. You actually have to take germs of functions. That is, we will identify functions if they are equal for sufficiently large value of the variable. So what we do is we take functions that are not really smooth, but for every n, there is some neighborhood of plus infinity where the function is n times differentiable. And so since we are identifying functions that are on neighborhoods of plus infinity, then it's a little bit like taking smooth functions. And so we'll take this differential ring, which is a quotient of this set under this equivalence relation. These are called germs at plus infinity. And we have the pointwise sum, pointwise product, and differentiation of germs as operations. So this is a differential ring. We are looking at Hardy fields, which are the differential subfields of G, this set of germs, which contain the field of real numbers identified with constant functions. And so taking this definition implies a lot of restrictions on the functions because, so as I said, the functions cannot have zeros. For germs, it means that they can have zeros, but they can have cofinally many zeros. So there must be some neighborhood of plus infinity where they have no zero, and since they are differentiable, they are continuous. So if they don't cancel themselves, then they can't switch signs. So germs must either be equal to zero on the neighborhood of plus infinity, or positive or negative on neighborhoods of plus infinity. So this tells us that we have another relation, which is just saying that a germ is smaller than another germ if this is true for sufficiently large value of the variable. And actually we have more because we want fields to be differentials of fields. So the derivative of the functions also must be of constant sign on neighborhood of plus infinity, which means that the function is either constant on a neighborhood of plus infinity or strictly monotonous, so strictly increasing or strictly decreasing. And so this tells us that functions in Hardy fields have limits in the extended real line, so either finite limits or minus infinity or plus infinity. And so using this, we can describe, first, we can describe the evaluation ring of such Hardy field. That is so in the context of valuation theory, which would be the germs that are finite, meaning that they are bounded by some constant function. And this is the same as asking the limit to be a finite one. And so this is a valuation subring of H, and we also have so the maximal ideal is described by taking functions whose limit is zero, which I call infinitesimal. So I'll first give some examples of Hardy fields. So first, the largest examples of Hardy fields are called maximal Hardy fields. So those are Hardy fields that cannot be contained in proper Hardy fields. You cannot extend them within the set of germs. So they exist by Zorn's lemma, but there is no constructive example, and there is no reason to believe that there would be an explicit example of maximal Hardy fields. They have some nice closure properties, and maybe they have more than that. So there is, for instance, an intermediate value theorem, but only of order 1, which is, so we have intermediate value theorem for differential polynomials of order at most 1. And I didn't mention it, but you also have, you can also solve f prime equal to g, and f prime is equal to f times g. So you have primitives, and you have exponential primitives. So you can show that this implies that maximal Hardy fields are closed, and so they contain the identity germ, so the identity function, the exponential function, the logarithm, and the iterates, and some other elementary functions such as the arctan function. And they're actually closed under composition with those functions because of the Van den Dries theorem. So now going back to the properties of Hardy fields, which is what we are interested in. So there are 3 main properties. Oh, I'm sorry, I ignored the chat until now. So one question was, why doesn't the conclusion include H? So we have two functions, 2 elements of Hardy field, f and h. The differential polynomial is negative at f and positive at h, and you just have a solution to the equation here that is just between f and h. The bounds are not so important, they must just exist. And so this is a separate set of solutions that we have. This is simpler to prove. So looking at this first property, so if you take a function which is a germ which is greater than the finite germs, then it must be strictly increasing, because otherwise it would be either constant, and then it wouldn't be greater than the constant that is itself, or it would be strictly decreasing, and so it would be smaller than some constant as well. So it must be strictly increasing, which means that the derivative must be positive. So we see that we have this property here. Second, if you take a germ in O, yes, sorry for the previous question. The germ G will depend on the polynomial, and since we are looking between f and h, it can depend on f and h, but not in a precise manner. Second, if you take a function which is a germ which is finite, then it has a finite limit, and so f minus that limit has 0 as a limit, and so it's infinitesimal. So this proves that this proves one direction, the other one is easier. That the valuation ring is the kernel of the derivative plus the maximal ideal. Finally, if you want to know how the derivative behaves on this one, if you take an infinitesimal germ, then it's not possible that the limit of the derivative would be other than anything other than 0, because if it were a real constant, then the function would be strictly decreasing and would tend to minus infinity or plus infinity, and the same is true for if it were minus infinity or plus infinity. So this shows that the derivative of the maximal ideal is containing the maximal ideal. So infinitesimals have infinitesimal derivatives. So if we abstract those three properties, we can look at differential ordered fields which satisfy those abstract properties. So sorry, I will just skip that. So those are called H fields, and with small derivation. I will most of the time just say H fields. Those were defined by Van den Dries and Aschenbrenner. So those are just other differential fields, such that setting O as so the set of elements that are bounded by constant element of the kernel of the derivation, and taking small o as the maximal ideal of big O, we have those three properties which are the same as I explained before. So Hardy fields are H fields, as we saw, and for just another example, which is similar but different, you can take formal Lorentz series. So you order them by saying that a series is positive if the first non-zero term of the series is positive. You get another field, and if you take the standard derivation, then you actually get an H field with small derivation, which is not, at least in a canonical or evident way, a Hardy field. So one other property that we must consider to start looking at equations on H fields is a UV closure. So I assume some people here are familiar with this, but we are in the ordered context, so it's a little bit different. So we say that an H field is UV closed if it is real closed first, and if we have so solutions to this type of equations. So we want integrals. It's just an integral, and here we want exponential integrals. So this equation here is the same as asking that the logarithmic derivative of y can have value t. So this is a UV closed fields, and if you UV closure are in some sense minimal extensions of H fields which are UV closed. I'm skipping a lot of interesting details here, but any H field, and in particular any Hardy field, has a natural UV closure. For H fields, there can be two UV closures, but I won't go to the details. So I try to present another example of H fields besides Hardy fields. This is our formal model. Those are transseries as defined by Dan Goering and Ekal independently. So there are formal series, so Hahn series to be precise, which involve so generalized power series, if you will. Yes, thank you, Nigel. So for Lorentz series, I gave the standard derivation that I gave is not small. It doesn't satisfy derivative of the ideal, goes into the ideal. You have to change it. So in general, if the derivation doesn't satisfy the third axiom of smallness, small derivative, then you can multiply it and you get the third axiom for free, or that easily. So transseries are just formal sums involving variable x, which is a sort of formal counterpart to the identity function, a variable logarithm log x, and an exponential e of x, which are just formal terms. They are not really functions. Then you can combine them in many ways. So, for instance, this is just log of log x. I just write log 2. So this is a transseries. And what is nice with transseries is that you have first an ordered field structure. The order is just given by ordering the different additively irreducible terms here, 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 and so on in an intuitive way. So exponential of x over n is much greater than log of x, which is much greater than 7, and so on. They also have, quite importantly for us, a derivation, which is a formal derivation. So to see how it works, you just take the series here, and you will differentiate each term in the intuitive way. So this one will be differentiated as this one. This one will be differentiated as this one, and so on. So this is cancelled. And so you commute with those infinite sums here. You also have a quite original, not so original in the realm of series, but you also have a composition law, which allows one to plug a series, so here log x, into another one. So I plug log x into f by just replacing the variable x by log x. And then I do some simplifications. For instance, exponential of log is just x, and so on. So this is just an example. You get this transseries. And so why do we care about the composition? Is that because it allows one to see each function, its transseries, as a function defined on transseries. So you take a positive infinite transseries G, you can plug it into F and you get a function which corresponds to F. And this function is actually really close to germs in Hardy fields. So for instance, if you fix a series G, then for sufficiently small delta, so for instance, if you take an infinitesimal that is very small, then you can obtain f around G, so close to G, by just doing Taylor approximations. But here, what is nice in a way is that you have a real equality. Yeah. And so using this, we can see that actually the formal derivation behaves like the real derivation of function. So this function is differentiable because if you have a Taylor series, then you are differentiable. And so actually this function is a germ of at plus infinity of a smooth function. It's not a real-valued smooth function, but it's close to it. And so using this type of analogy between germs and transseries, you can prove that transseries are an H field with more derivation. So you can do basically the same proof as we did before. And so you also have nice closure properties. The first one is it is UV closed. So you can do this in two steps. First, the derivation is surjective. It's not really difficult to prove, but it's because you have to. It's difficult in a formal sense, but it's very intuitive. It's nothing to do. And you also have an exponential function, which which is an isomorphism between the additive group and the multiplicative group of positive elements, and it respects the order, it's strictly increasing. And so you have a compatibility between the derivation and the exponential. So you have a chain rule for where you would expect that the derivation of the derivative of x is x itself.
Vincent? Vincent,
Yes.
sorry to interrupt. So we're
Yeah.
running a little low on time.
Okay.
So maybe if you could manage to come to the main result and finish the first part of the talk in, say, maybe 5 minutes, and then we can come back to the discussion after the breakout rooms.
Okay. So yeah. Thanks. Yeah, and so since you have surjective derivation, which means that you have integrals, and you also have an exponential, this allows you to solve those the equations for UV closure. And so you can obtain that this field is UV closed. So to conclude on the properties of transseries, the model theory as a valued differential field is known. So this is work of Aschenbrenner, Van Andries, and Van der Hoeven, which I will just call ADH in a second. So you have very strong properties for the theory, which is that the complete theory is model complete first, which means that in particular transseries are existentially closed. So every solution in extensions of transseries to differential equations already have solutions in transseries. Furthermore, you have quantifier elimination results in an extension of the language of differential order fields. And you have an axiomatization. So the theory is decidable. I will give the axiomatization in a moment. So the relationship between transseries and Hardy fields. One of the relationships is this conjectural property that is that the authors expect that Hardy fields have the same theory, first order theory, as transseries. So although maximal Hardy fields, sorry. So although maximal Hardy fields are somewhat complicated analytical objects that are hard to even to have intuitions about, maybe they could be described using transseries instead. So maybe you could have sort of bridges between transseries and Hardy fields. So as I said, one way to axiomatize this theory is to ask for axiom of H fields, UV closed H fields with more derivation, and to put the intermediate value theorem. So transseries satisfies satisfy the general intermediate value theorem for differential polynomials. So which means that the conjecture here is equivalent to the fact that to the conjecture that maximal Hardy fields also satisfy this intermediate value theorem. So in the sequel I will talk about my work regarding surreal numbers and their relation to H fields.
Okay, so thanks for the very nice first part of the talk. There were some questions in the comments already. I think they've been answered. Are there any further questions?
What is the natural language?
So yeah, so we have to go into details a little bit. One important properties of transseries is that you have those terms here. So you have x, log x. Sorry, you have all those iterates of log n x in general, and every positive infinite transseries is smaller than some of those, one of those. So for every f this positive infinite, you can find something that is smaller that is of this sort. In a way, every function that tends to infinity is greater than some iterate of the log, or every common function. And so this implies that because of the properties of the derivative, that if a function has a positive derivative, for instance, then the function must be greater than such products. So this will be smaller. And so this tells you that you have cuts in transseries. That is, so you have some initial, for instance, initial subsets for the order that don't have a suprema, that are holes in transseries, which corresponds to the absence of corresponds to the fact that transseries are closed under many equations, and so you need to add some of those cuts as primary element in the language, so as a unary how do you say it? Unary relations in the language, and then you can state everything that should be which cuts should be filled and which cuts shouldn't be filled, and then you fill the gaps in the theory with just this language. I think I wasn't very clear, but I can expand maybe.
Thanks.
Okay, are there any further questions? Okay, so if there's no further questions at the moment, I suggest we move on to the breakout rooms.
I will try to be quicker and try to explain what my work is. So feel free to interrupt and ask questions on the chat or already. So the next step is theory of surreal numbers. So if you don't know what they are, so surreal numbers are an ordered field defined by Conway, which can be represented as this large complete binary tree. So a tree where each node has two successors and one left and one right, and going on the right you get bigger, and going on the left you get smaller. So this is just half of the picture, but so you take the full binary tree where you don't stop at finite depth, but you also go beyond. So you take ordinals to go beyond. And so it is lexicographically ordered, meaning that if you want to know if 1/2 is greater than 3, for instance, you just compare 3 and 1/2 to their last common ancestor, which is 1. And so this is smaller than 1, and this is greater than 1. So this is smaller than this, for instance. And you also have simplicity relation, which is just the fact that there be paths from between nodes in the tree. So we say that 1 is simpler than 4 because there is a path from 1 to 4 in the tree, for instance. And 3/4 is simpler than this one number here. So Surreal numbers have a defining property, which is how Conway defined Surreal numbers, which is that if you take sets of Surreal numbers L and R for left and right, where everything in L is smaller than everything in R, and there's something that is between the sets. So there is a number written like this, which is between L and R. And there's also a simplest one that is a minimal for the simplicity relation, a unique minimal one. So this is nice because this allows one to define a lot of structure on Surreal numbers in the following way. So for each number A, we will consider the set of numbers so B that are strictly smaller and simpler. We write it AL for left, and AR will be the set of numbers that are strictly larger and simpler. And so, for instance, A lies between AL and AR by definition, and it's also the simplest that lies between AL and AR. And so if you want to define a function on A, so f of A, we can do it by specifying what is f on this set and what is f on this set. So we have predictive definitions. When we use this to define a product and a sum and a product and the other structure on NO on Surreal numbers. So just quickly, if we want to define the sum of two numbers, we do it by induction. So we assume that we know that this is defined and this is defined. So for every B in AL, for every C in AL, C plus B is defined. So we know that everything in AL is smaller than A, everything in BL is smaller than B. And so, conversely, we have those relations here. And so we should have that everything here is smaller than A plus B, and everything here is smaller than A plus B, and so on. So we can say, okay, let's define A plus B as the simplest number, which is greater than those, which are smaller, and smaller than those. And it actually works, gives you a nice law of order group. And so you can find similar equations for the product, inverses, and opposites. And you get a real closed field, which contains a field of real numbers in a canonical way. So Conway defined further structure on Surreal numbers, which essentially showed that it is a field of Hahn series. That is, every number can be written as a sum, an infinite sum, or finite or infinite, where the terms here are specific numbers called monomials, and the terms here are just real numbers. And another author, also Gunshaw, defined exponential function on NO, so an isomorphism from additive group to the multiplicative group of positive elements. And you actually obtain a model of the real exponential field doing this. And you use also a simple equation. So if you have an exponential, a logarithm, because you have it's deductive, and you have Hahn series, you can actually have it's similar to transseries. So if you take a number A written as a Hahn series, you can replace each monomial m here by exponential of gamma, where gamma is just the logarithm of m. And so you get a sort of transerial representation of numbers. Just playing with notations here. And actually, using this, you can embed transseries in real numbers. So you identify omega with the transseries x. Omega is a specific surreal number. Then you close under sums and the logarithm and exponentials, and you get a copy of transseries. So now we would like to use this transerial representation to define derivations on NO that turn it into an H field. So this was done by Veratucci and Mantova. So they find a derivation that turns NO into UV closed H fields. So to explain how it works, you take a number A written as a transseries, and you want to define the derivative. But what you want to have is that the derivative of the exponential of gamma should be the derivative of gamma times exponential of gamma. And so actually what you want to do is only define the derivative at gamma, at exponents. But exponents are numbers as well. So if you go up in the expansions, you only have to the only case where you don't know how to define the derivation is when gamma is written as exponential of a monomial, which is itself is an exponential of a monomial, and so on. So this is a case of numbers that are whose logarithmic iterates are monomials. And so if you define a derivation on this class of such so-called logarithmics with a few inequality conditions, then you have a derivation on NO which has nice properties. The one problem is that there are a lot of numbers like this, so those logarithmics, and so there are many ways to define the derivation, but Berarducci and Mantova found the simplest way to do it. And so later, ADH proved that actually you have a model of the theory of transseries. So this is a really good derivation on NO, which turned it in a nice model for H fields. One problem is that you don't have the thing that we had earlier with seeing transseries as functions. So the Berarducci and Mantova prove that you don't have a position law on NO that would be compatible with the derivation that would satisfy the same properties. So what I'm doing is trying to find another derivation that would satisfy this. So to do this, I look at other type of functions besides exponentials. So hyperexponential is a solution to this equation, which is if you add 1 to the argument, an exponential comes out. And it was proved by Kneser that there is a strictly increasing analytic function which satisfies this. And by virtue of the equation, such function must grow very quickly. Because so if you grow a little bit in the argument, you grow a lot, actually. And so actually these functions, those hyperexponential form Hardy fields. Yeah, I will just skip this. And so those are natural elements that appear in maximal Hardy fields. Maximal Hardy fields will have those type of really fast-growing functions. So if we want to use Surreal numbers to describe functions, we can try to have those functions on Surreal numbers. So we did this with Van der Hoeven and Mantova. We defined a sort of Surreal version of the hyperexponential, which is a strictly increasing bijection between so positive infinite Surreal numbers, which is greater than every finite iterate of x, which satisfies the equation, so the same equation as before, and it also has low expansions, as we saw with the transseries. We can actually do, we can generalize this to even faster growing functions that I call e omega to the mu, so these are ordinals, which satisfy the same equations, but instead of having just x here, you have a omega mu. So really, really, really fast-growing functions. And you have sort of natural relations or natural ways to define the derivative and of those functions. If you take the functional inverse of those functions, the derivative is given as a transfinite product of previously defined functions. This is a sort of generalization of the derivative of log n, so which is just this. So using this, we can write Surreal numbers not as transseries, but as sort of hyperseries, which are series involving those hyperexponentials. So to do this, you take a monomial and you will write it, you will expand it in a unique way as a sort of product of two hyperseries, so Fn and Fr. And then if you want to define the derivative of m, you just use the derivative of Fl and the derivative of Fr, the derivative of phi here and the derivative of u. And so previously, you only have to know the derivative of phi and u because those one are given by the nature of those series. So if you fix that the derivative of omega is 1, because it's like the identity function, then we only have to look at some infinite expansions, which are sort of canonical representative of certain cuts. And for those, what is nice is that you can take syntactic derivatives. That is, you want the derivative of m to be the derivative of this one, which is m1, times the derivative. My formula is so sorry. So the derivative of m would just be the derivative of m1 times exponential of m1. So okay. So anyway, what you get if you do this and you expand the derivative of m1 using m2 and so on, you get an infinite sum, which will have a limit, say, and this infinite sum works in the sense that it satisfies the chain rules that you want to have for the derivation. So using this, I'm proving that there is a function on NO which is a derivation with the same properties as Raducci and Mantova's derivation, but this one has one advantage, which is that it commutes with those hyperseries here. And so we think that having defined those series, those derivation, we circumvent the problem of incompatibility between derivation and composition. So what I mentioned here, we think that this one is compatible with seeing numbers as functions. So the goal of my PhD is to prove that you can see numbers as functions, and those functions should be similar to germs in Hardy fields. Okay, so now I'm done.
All right, so thank you. Do we have some questions, comments? Okay, so if there's no questions, then
I might have a question.
Okay.
Yeah, it's a bit technical. I was wondering about these two functions FL, FR, which is like if m is omega, how would that look like, for example?
Yes, so this is a way to decompose monomials, so numbers, as hyperseries apply to simpler numbers. So ideally, we would want this one to be simpler than m, and this one to be simpler, so that we can proceed inductively by doing those expansions. And so omega is the simplest positive infinite number. And so this one would just be written as, so for omega, it would be omega equal omega. So in this case, we take FL is equal to 1, I guess, and U is equal to omega, and FR is equal to identity, X. So,
I see. I see. Okay. No, thank you. Okay, I understand now. Okay, thank you. Yeah, yeah.
But I'd say in almost any other case besides omega, you get something simpler.
Any further questions, comments? All right, so if not, then, well, let's thank Vincent again. And yeah, so we're looking forward to seeing you all again next week then.
Right.
All right, thank you. Bye-bye. Take care, everyone.
Thanks, Vincent. Thanks, everyone.
Thank you.